Okay, let's take a look at review problem 16. We have a die that's rolled twice. X will be the number of times it lands either 1 or 2, and Y will be the number of times it lands 3, 4, or 5. And clearly there is a third possibility, namely that it could land 6. Find the joint distribution of X and Y. Well, there are 6 ways this can happen. You can have X equals 0 and Y equals 0, so that they both land 6. Or you could have X is equal to 0 and Y is equal to 2, or Y equals 1. You can have X equals 0 and Y equals 2. You can have X equals 1 and Y equals 0. You can have X equals 1 and Y equals 1. And lastly, you can have X equals 2 and Y equals 2. Those are the Y equals 0. Those are the 6 ways you can have X equals something and Y equals something, where X and Y are both positive, and the sum of X and Y is less than or equal to 2. Okay, so for this one, there are 0 1s and 2s. There are also 0, 3, 4s, and 5s, which means they're all 6s. So using the multinomial distribution, that's 2 factorial over 0 factorial, 0 factorial, and 2 factorial for the number of 6s, 1/3 to the 0, 1/2 to the 0, 1/6 to the second. And that works out to be 1 over 36. Next, the chance that there are 0 1s and 2s, there's a 3, a 4, or a 5. That means there also must be a 6. So by the multinomial distribution, we have 2 factorial over 0 factorial, 1 factorial, 1 factorial, 1/3 to the 0, 1/2 to the first, 1/6 to the first, and this works out to be 1/6. Next, 2 factorial over 0 factorial, 2 factorial, 0 factorial, times 1/3 to the 0, 1/2 to the second, 1/6 to the 0, and so this works out to be 1/4. Next, we have a 1 or a 2, so 2 factorial over 1 factorial, 0 factorial, 1 factorial, 1/3 to the first, 1/2 to the 0, 1/6 to the first, and that simplifies as 1/9. Next possibility, 2 factorial over 1 factorial, 1 factorial, 0 factorial, 1/3 to the first, times 1/2 to the first, times 1/6 to the 0, and that works out to be 1/3. And the last possibility would be 2 factorial over 2 factorial, 0 factorial, 0 factorial, for 1/3 to the second, times 1/2 to the 0, times 1/6 to the 0, and that works out to be 1/9. And if I add all 6 of these fractions up, I had better get 1. Next, let's figure out the marginal distributions of X and Y. First, let me do it the brute force method, and then we'll talk about how this could have been done without brute force. For the marginal distribution for X, there are 3 possibilities. X could be equal to 0, 1, or 2. X equals 0 would be the top 3 possibilities here. So that would be 1 over 36 plus a 6th plus a 4th. X equals 1 would be these middle 2 possibilities, 1/9 plus a 1/3. And X equals 2 would just be the last one, 1/9. And that works out to be 4/9, and this one also works out to be 4/9. For the marginal distribution for Y, there's also 3 possibilities. Y could be equal to 0, Y could be equal to 1, or Y could be equal to 2. Y equals 0 would correspond to the first, 4th, and 6th possibilities. 1 over 36 plus 1/9 plus 1/9. Y equals 1 corresponds to this possibility, 1/6, and also this one here, 1/3. So 6 plus a 1/3. And Y equals 2 would correspond to this third one, which would be just a 4th by itself. This works out to be 1/2, and that also works out to be 1/4. And so those are the marginal distributions for X and Y. It would have been a whole lot easier if I had said at the top that X is binomial with parameters 2 and 1/3, while Y is binomial with parameters 2 and 1/2. Now, why in the world could I just simply write that down without doing all this previous work? Well, we remember that we have a fair die that's being rolled. X is the number of times it lands 1 or 2. Forget about Y. X is the number of times it rolls 1 or 2. So there's 2 attempts, and the chance of success is 1 out of 3, 2/6. For Y, there's 2 attempts, and the chance of success would be 3 out of 6. And so it stands to reason that X is binomial with parameters 2 and 1/3, while Y is binomial with parameters 2 and 1/2. Okay, number 3. Let's find the conditional distribution of Y given that X is equal to little x. Now, there are 3 possibilities for little x. X could be equal to 0, 1, or 2. So let's list out all those possibilities. So if x equals 0, there are 3 possibilities. You could have y could be equal to 0, given x equals 0, or you can have y is equal to 1, given that x equals 0, or you can have y is equal to 2, given that x equals 0. The chance, each of these is found by division, so that's the chance that x equals 0 and y equals 0, divided by the probability that x equals 0. This one is the probability that x equals 0 and y equals 1, divided by the probability that x equals 0. And the last one is the probability that x equals 0 and y equals 2, divided by the probability that x equals 0. Okay, the chance that x equals 0 is 4/9. So that's the same for all 3 of these. The chance of x equals 0, y equals 0, and so on, that's going to be 1/36, 1/6, and 1/4. So 1/36, 1/6, and 1/4. And so this works out to be 1/16. This works out to be 3/8, and this works out to be 9/16. So that's if x equals 0. Let's start over again, and suppose x is equal to 1. If x equals 1, there are 2 possibilities for y. You can have y equals 0, or you can have y equals 1. So that would be the probability that x equals 1 and y equals 0, divided by the probability that x equals 1. You also have the probability here that x equals 1 and y equals 1, divided by the probability that x equals 1. The chance that x equals 1 is 4/9. So we have over 4/9 for both of these. And for the numerators, we go back to the top. The chance that x equals 1 and y equals 0 is 1/9. The chance that x equals 1 and y equals 1 is 1/3. So I have 1/9 here and 1/3 here. So this works out to be 1/4, and this works out to be 3/4. And lastly, we look at x equals 2. There's only one possibility, y equals 0, given x equals 2. Now, the calculation here is a bit silly, but let me do it for the sake of completeness. Chance that x equals 2 divided by, and y equals 0, divided by the chance that y equals 0. I'm sorry, divided chance that x equals 2 on the bottom. The chance that x equals 2 is 1/9, and also the chance that x equals 2 and y equals 0 is the same 1/9. And so this works out to be 1/9 divided by 1/9, which works out to be 1. Okay, so that is the conditional distribution of y given that capital X is equal to x. Now, it turns out that there is a shortcut way to be able to do all of these without doing the brute force. We'll talk about that in a couple of minutes. Problem number 4. Find the conditional distribution of x given that capital Y is equal to little y. All right, this is going to be very much the same as before. So there are 3 possibilities for little y. You can have y equals 0, or y equals 1, or y equals 2, and we will consider those separately. For y equals 0, there are 3 possibilities. X equals 0, or x is equal to 1, or x is equal to 2. Those are the three possible values of x if y is equal to 0. So that's the chance that x equals 0 and y equals 0 divided by the probability that y equals 0. This one is a probability that x is equal to 1 and y equals 0 divided by the probability that y equals 0. Last one is a probability that x equals 2 and y equals 0 divided by the probability that y is equal to 0. Okay, now we refer back to previous work. The chance that y is equal to 0 we found earlier to be 1/4. And we found up here the chance that x equals 0, y equals 0 is 1/36. Then the other one is 1/9, and the next one is also 1/9. So all of these are over 1/4. And the numerators are 1/36, 1/9, and 1/9. So the top one is 1/9. Then the bottom two are the same, 4/9. So that's the conditional distribution of x given that y equals 0. Next, let's find the conditional distribution of x given that y equals 1. There are two possible values of x. X could be equal to 0, or x could be equal to 1. So that's the probability that x equals 0 and y equals 1 divided by the probability that y equals 1. This one is a probability that x equals 1 and y equals 1 divided by the probability that y equals 1. Okay, now let's flip back to what we did earlier. The chance that y equals 1 is a half. The chance that x equals 0 and y equals 1 is a sixth. The chance that x equals 1 and y equals 1 is a third. All of these are over a half. The numerator for this one is a sixth. The numerator for this one is a third. So this works out to be 1/3. This works out to be 2/3. Lastly, there is one last possibility. Y could be equal to 2. If y equals 2, then there's only one possible value for x. Y equals 0. Now this is again silly, but let me do it for the sake of completeness. X equals 0, y equals 2, divided by the probability that y equals 2. The chance that y equals 2 is 1/4, and the chance that x equals 0, y equals 2 is the same 1/4. So this works out to be 1/4 over 1/4, which is 1. Okay, so there are the conditional distributions for capital Y, given the conditional distributions for capital X, given the values of capital Y. All right, now I said earlier that there was a shortcut way to do this, and here's the shortcut. It turns out that these follow the binomial distribution with parameters 2 minus x and 2/3. Or sorry, 2 minus y and 2/3. Okay, now let's check this actually works. If y equals 1, then you have 1 trial, 2/3 chance of success, so 2/3, 1/3 makes sense. If y equals 0, so that you have 2 trials, then the chance of 2 successes would be 2/3 squared. The chance of 0 successes would be 1/3 squared. And the chance of 1 success would be 2 times 2/3 times 1/3. So it works out again. Now, why in the world can I just simply write that down as my answer without doing any work? Well, remember, there are 6 possibilities when I roll the die, and I am given the value of capital Y. So I'm given the number of 3, 4s, and 5s, so those go away. So I have 2 minus y attempts, whatever y is, the number of 3, 4s, and 5s. And so that's the number of attempts. Given, if I know full well that it's not a 3, 4, or 5 for what's left, then there's a 2/3 chance of being a 1 or a 2 if I know that I've eliminated all the 3, 4s, and 5s. So that's binomial 2 minus y 2/3, and I can just simply write that down without doing in all these calculations. Similarly, for the previous problem, we had this big list of conditional distributions. By the same logic, there are 6 possibilities when I roll the die. 1, 2, 3, 4, 5, 6. I am counting up the numbers of 1s and 2s, and then I throw them away. So if I take away all the 1s and 2s, of the 4 possibilities, 3 are favorable for being for y. And so these are going to be binomial with parameter 2 minus x. I take away the number of 1s and 2s, and then 3/4. And if I actually check this, then the probabilities that I see here, if x equals 2, if x equals 1, or if x equals 0, I get the binomial distribution with parameter 2 minus x and 3/4. Okay, continuing. Number 5, find the correlation coefficient of x and y. To find the correlation coefficient of x and y, I need a few things first. The expected value of x is 2 times a third, because x is binomial with parameters 2 and 1/3. So that's 2/3. And the expected value of y is going to be 2 times a half, because y is binomial with parameters 2 and a half. The standard deviation of x is the square root of 2 times p times 1 minus p, and that works out to be 2/3. And for y, the standard deviation of y is the square root of n times p times 1 minus p, which is 1 over the square root of 2. Okay, now the next thing that I need is the expected value of x times y. The expected value of x times y. So to do this, let's take a look back at the work that we did earlier. So here are the probabilities from part 1. So I take x times y, 0 times 0, times the probability. Next, x times y, times the probability, 1/6. Next, x times y, 0 times 2, times the probability, 1/4. Then 1 times 0, times the probability of 1/9. Then 1 times 1, times the probability, 1/3. And lastly, 2 times 0, times the probability, 1/9. So take x times y, times the probabilities for each. Clearly, the only term that contributes is going to be the one that I just underlined, and so the expected value of x times y will work out to be 1/3. Okay, so to find the correlation coefficient, we next find the covariance of x and y. The covariance of x and y is expected value of x times y minus the expected value of x times expected value of y. So that's equal to 1/3 minus 2/3 times 1, which is negative 1/3. And finally, the correlation between x and y will be equal to the covariance of x and y divided by the standard deviation of x times the standard deviation for y. So that's negative 1/3 over 2/3 times 1 over the square root of 2. And simplifying, we get this is equal to negative 1 over the square root of 2, or approximately negative 0.707. So the answer is negative. Does this make sense that the answer is negative? Well, if x is large, if there are a lot of 1s and 2s, then there can't be a lot of 3, 4s, and 5s. Likewise, if there are a lot of 3, 4s, and 5s, then there can't be a lot of 1s and 2s. So x is large implies y is small. If y is large, that implies x is small. And so that is evidence to think that the correlation coefficient must be negative.